We are going to take multi-view videos as inputs and turn them into a volumetric free viewpoint video. We call this HyperReel. HyperReel can render novel views of dynamic scenes at megapixel resolution, allowing interactive visualization without custom CUDA code and baking. Recent works have explored various representations for 6-dot videos, but balancing speed, quality, and memory remains challenging. Let's start with rendering this T-Rex. To render a single pixels, we need to sample hundreds of 3D points on an array. For each point, we query a trained neuron field to obtain the density and the RGB color viewing from a specific direction. This is wasteful because many of the sampled 3D points are in empty space and do not contribute to the final color. One can accelerate this process by predicting the densities of these samples. By thresholding the predicted density, we can reduce the number of required evaluations per array. Our idea is to directly generate a sparse set of samples. We optimize the sample prediction networks to produce the parameters of geometric primitives, such as planes or spheres, and find the samples by intersecting the array with the primitives. This design makes the training much easier because the sample prediction network only needs to predict one primitive for all the rays passing through the same point. We further predict point offsets to capture challenging view-dependent effects such as reflections and refractions. These designs lead to higher fidelity reconstruction. How about memory efficiency? The neural fields takes a continuous 3D position and viewing directions as inputs and produce the corresponding RGB color and volume densities. We build upon TensorRF, which models the scene by factorizing the tensor into multiple compact low-rank tensor components. For dynamic scenes, we extend TensorRF to factorize the space and time volume. But this remains memory-intensive for one video. We can borrow insights from compression algorithms for 2D videos. These measures encode a set of keyframes or iframes by leveraging spatial redundancies, and encode the nearby frames or p-frames with temporal prediction. Following this idea, we model keyframe volume and interpolate the intermediate frames using trainable scene flows. The resulting memory footprint for modeling the entire video is similar to a TensorRF used for a single static frame. HyperReel achieves fast rendering, high-quality reconstruction, and memory-efficient modeling. Let's take a look at some results.